Today we are Group 2 from BSIS 2B. Today we will demonstrate the shell sort algorithm. And now let's move on to shell sort overview. Shell sort was introduced by Donald Shell in 1959. It improves insertion sort by using a gap. This gap allows us to compare elements that are far apart. Each round, the gap gets smaller until it becomes one.
We will simulate shell sort using mathematical data. These are the ordered values. We will sort them step by step.
Now we begin the actual shell sort process. The first thing we choose is the gap. And for our first round, the gap is 4. Since our gap is 4, we compare the first number with the fifth, the second with the sixth, the third with the 7, and so on. So let's start comparing. First, comparison 58 and 63. Since 58 is already smaller than 63, they are in the correct order. No need to swap. Always remember, if the left number is smaller, we keep it as is. Next comparison 22 and 45. Again, these are already in the correct order. We leave them. Now we compare 91 and 28. This time, we clearly see a problem. 91 is way too big to be here, and 28 is supposed to be much earlier in the list. Because 28 is smaller, we swap 91 and 28. This is exactly what the shell sort is good at, moving big misplaced numbers much closer to where they belong. Our last comparison for this gap, 17 and 34. These are correctly arranged, so no swap is needed. After finishing gap 4, our list now becomes 58, 22, 28, 17, 63, 45, 91, and 34. Notice how this already looks cleaner. The biggest problem, 91 has been pushed closer to the back, and a smaller number 28 moved forward.
Now that the large mistakes are fixed, we reduce the gap. The next gap is 2. This gap let us compare numbers that are 2 spaces apart. At this stage, the goal is to tighten the order and bring similar size number closer together. With gap 2, we compare. First with third, second with fourth, third with fifth, and so on. This helps smooth out any medium-sized mistake in the list. First comparison, 58 and 28. 28 is much smaller, so it clearly should be earlier. We swap them. Next comparison, 22 and 17. 17 is smaller, so we bring it up by swapping the 2. Now we compare 58 and 63. These are correctly arranged, so no swap is needed. Still in proper order, the 22 and 45. Now, 63 and 91, also correct, so we leave them as is. Final comparison for gap 2, 45 and 34. 34 belongs earlier, so we swap them. After completing gap 2, our list now looks like this: 28, 17, 58, 22, 63, 34, 91, 45. We are very close to a fully sorted list now.
Now our gap becomes 1. This is the final phase of shell sort, where the algorithm acts exactly like insertion sort. But notice something. The list is already partly sorted because of the earlier gaps. This means insertion sort will only require small movements, making the sorting faster. We go through the list one element at a time and insert each value where it belongs in the growing sorted part on the left. So let's start. First is 28. It's the first element, so it stays where it is. Next is 17. 17 is smaller than 28, so we move it to the front. Now is 58. It is already larger than both 17 and 28, so nothing changes. Next, 22. It is smaller than 58 but larger than 17, so we place it between 17 and 28. Now, 63. It is larger than all previous numbers, so it stays in place. Next is 34. It belongs between 28 and 58, so we insert it right there. Now, 91. It is the largest number so far, so it stays where it is. Finally, 45. It is smaller than 58 but bigger than 34, so we place it between 34 and 58. And now, the list is fully sorted, which is 17, 22, 28, 34, 45, 58, 63, and 91.
This completes our shell sort demonstration. By starting with large gaps, shell sort fixes big mistakes early. As the gaps become smaller, and list becomes more and more organized until the final insertion sort finishes everything cleanly. Shell sort is efficient for medium-sized data and reduces the number of movements compared to simple sorting algorithms.
So let's talk about shell sort's time complexity. So what makes shell sort interesting is that it doesn't have just one time complexity. Its speed actually depends on a single idea that guides the entire algorithm, which is the gap sequence, or how far apart the compared elements are. With that in mind, let's go through each case one by one. Now, let's start with the best case. Shell sort can be extremely fast, running at of n log n, when the gaps are chosen wisely. In this situation, the early phases using large gaps almost fully organize the list. So by the time the algorithm finishes with a gap of 1, the list is already close to sorted, and the final insertion phase becomes very light work or easy to work. Think of it like you clean a room that's already nearly organized, and you only need a few quick adjustments to finish it. Now, moving smoothly to the average case, most of the time shell sort runs around of n to the point of 5. This happens because the algorithm reduces big mistakes early, and each gap pass brings the list closer and closer to order. So even though it's not fully sorted right away, each pass is easier than the one before it. And that gradual improvement leads to better speed time than classic O and squared algorithms. In short, shell sort gets faster as it goes because each gap prepares the list for the next one. However, there's a slow side, which is the worst case. Shell sort can take O and squared. This usually happens when the original gap sequence, like dividing gap by 2 every time, so it doesn't spread the comparisons efficiently. When that happens, shell sort starts behaving like a slower insertion sort, doing many extra comparisons and shifts. So yes, shell sort can be slow, but only if the gaps aren't chosen well. So to solve that problem, researchers designed better gap sequences. And this is where shell sort really shines. So this improved gaps shell sort These improved gaps help shell sort fix problems much faster, especially in the early stages. So what we call this is of n to the 4 thirds and of n log squared n. With these sequences, shell sort becomes significantly more efficient and can even compete with some more advanced algorithms on medium-sized data. So to bring everything together, best case is of n log n, average case is n to the 1.5, worst case is of n squared, then improved gaps is n to the 4 thirds and n log squared n. Overall, shell sort becomes faster when the gaps help fix the big mistakes early. This makes it more efficient than simple sorting algorithms, especially when working with small or medium-sized data or datasets. That's the time complexity of shell sort. Flexible, powerful, and surprisingly efficient when used with the right gap sequence. Now let's go through the shell sort code that produces the gap by gap output. I will explain each block of code so you can understand how the program works. So, this block of code means this method ensures that the program accepts numbers only. If the user types something invalid, the program won't crash. Instead, it shows an error message and asks again, which is the while true loop. Keeps repeating until the input is valid. Next is the print array method. This one. So this is just a helper method that prints the entire array on one line. We use this every time we want to show the array after each gap. Next is the shell sort method or gap only method. So we create the shell sort method which receives the array to sort. We store the length of the array in n, which is this int n. So and we print a header to show that the algorithm has started. Next is the gap loop, which is this one. So this is the main loop of shell sort. The gap starts at halfway the array size, then becomes smaller each round until we reach a gap of 1. We also print the current gap so the user knows which pass is running. Next is the gap insertion sort, which is this one, this block of code. So inside the gap loop, we perform a gap insertion sort. So here's what happens. So that temp, which is this one, stores the current element we want to insert, and J, which is the J is used to shift elements until we find the correct spot. The inner while loop, which is this one, checks whether the element behind the current one is larger. If so, we shift elements right until we find the correct place to insert in the temporary data in here. Next block of code is print array after each gap, which is this. The function of that is, after finishing the entire pass for a specific gap, we print the array so the user can see how the list changed. This gives a clean, easy to understand output for gap 4, gap 2, and gap 1. Next is the main method, which is ang user input, this one. So the main method starts the program. We create a scanner to read input from the user. Next is ask for number of elements, which is this one. So here we ask the user how many elements they want to sort, and we use our safe input method to ensure only numbers are allowed. Next is read all elements safely, which is this one, this block of code. We now create the array and ask the user to enter each number again. Every input is validated for safety. Next is the print original array, which is this one. The purpose of that is to print the original array. Next is run shell sort. So this one. Now we call our shell sort method, which performs all the gap passes. And this is the final sorted array. This shows the output of the sorted array or the final sorted array. So let's run the code. So let's use the example in our document as our example today in our code. Is 8 elements. First number is 55, 22, 28, 17, 63, 45, 91, and 34. As you can see here, because the array length is 8, the first gap is 8 divided 2 equals to 4. So gap equals 4, so 4 position apart. So after comparing, this is the output for gap equals to 4. Next is gap equals to 2. Since the next gap is equals to 2, next gap is equals to 4 divided 2 equals to 2. This 4 divided equals to 2 is 2 positions apart. That's the output for graph number 2. Next is gap equals to 1. Since final gap is 2 divided 2 equals to 1, so this is an insertion sort, or where you compare them behind the element. So it compares like this. It starts with the first index and compares to previous index. That's just the function of insertion sort, and that is the output for the gap equals to 1 sorting, and the final output becomes this one, which is the sorted output. As you can see here, it's now sorted from smallest number to biggest: 17, 22, 28, 34, 25, 55, 63, and 91. And that's all. Thank you.
Shell sort perform less algorithmic arithmetic, even reverse data improved quickly due to early dump corrections. Shell sort has strong performance on small and medium lists while using medium memory, but its speed depends on the gap sequence.
This concludes our shell sort algorithm demonstration. Thank you for watching.